Our next topic is one that's familiar to us but requires a surprising amount of care when working with things very, very carefully and using the axiomatic approach that we have been. And that is circles. We're going to define them and look at some of their various properties and how we can work with them. So, definition 96. Given a plane E, a point P that lies inside E, and a positive real number R, the circle with radius R and center P is denoted C of P and R. Usually the plane that everything lives in is suppressed from the notation, and it's defined to be the set of all points Q in the plane such that PQ equals R. So it's the standard definition of a circle. It's the set of all points that are the same distance away from the point P, your fixed distance. We've got some other notation and terminology to use here. Two circles with the same center and therefore necessarily different radii are called concentric, meaning same center. If Q is in the circle with center P and radius R, then the segment PQ is a radius of the circle CPR, and Q is called the outer end of that radius. We will often talk about the radius of a circle. When we talk about the radius of a circle, we mean the distance from the center of the circle to any point on the circle. When we talk about a radius of a circle, we're talking about a segment that goes from the center of the circle out to some point on the circle itself. If Q and R are 2 points in the circle with center P and radius R, then the segment QR is a chord. Well, let me do that better. Is a chord of the circle CPR. And then if if Q and R are in the circle with center P and radius R, and P is in the chord QR, then the segment QR is called a diameter of the circle with center P and radius R. And again, we talk about a diameter of a circle, meaning one of these line segments that goes across the circle contains the midpoint, or we might talk about the diameter of the circle, and the diameter would be the length of a diameter. That doesn't come up too terribly often. Usually we use the radius more than we do the diameter. And then finally, the interior of the circle with center P and radius R is the set of all points Q in the plane such that the distance from P to Q is less than R. And the exterior of the circle with center P and radius R is the set of all points in the plane where the distance is greater than R. So these are all fairly standard pieces of notation. Let's go ahead and illustrate all of these pieces for the sake of completeness. So we've got a point P here. The circle with center P and radius R is going to be all the points on the edge of the circle. If we take a point Q over here, this segment is a radius of the circle. Q is the outer end of that radius. If I've got another point R over here, then this segment, let's actually get the segment. This segment is a chord if one of these actually goes all the way across. Then that gives us a diameter. And then the interior of the circle is all this stuff here, whereas the exterior of the circle is all the points that are further than r away, than little r away from the center. So all perfectly standard terminology here. Another piece of terminology that isn't quite as standard in terms of geometry, but is familiar to us from calculus, is the following. If a line L is coplanar with a circle CPR, and the size of the intersection between L and CPR is 1, then L is tangent to the circle with center P and radius R. So a line that is tangent to the circle is one that will intersect the circle in exactly 1 point. So here is a line tangent to the circle, or a tangent line to the circle. Oh, sorry, this is definition 97. And then if a line L intersects CPR in more than 1 point, it is called a secant line. So the red line here is a tangent line, whereas the white line is a secant line. So one that intersects the circle in more than 1 point. Now, one of the things that we're about to prove is that a secant line, in fact, intersects the circle in exactly 2 points. It can never intersect it in more than that. So the first thing that we want to consider is when a line is tangent to a circle. We want to get some equivalent form of that we can work with to detect when a line is tangent or not. So that's theorem 98. So let C be the circle CPR, L a line coplanar with C, and let's suppose that Q lies in the intersection of L and C. So we're assuming that there's some point that is in both L and C. So the line intersects the circle in at least 1 point. The following are equivalent. Part 1, L is tangent to C, which means that the intersection is only the point Q. That's equivalent to the statement that the line PQ is perpendicular to L. This is a very a good way of describing tangency that connects it up with many of the other things that we've done. Perpendicular lines are nice because they form right angles. We've got lots of theorems about right angles and how to use them. So let's look at the situation at hand and see what we want to work, see how we want to work this. So we've got a point P and we've got a point Q, and then we have a line L, and what we know is that it intersects the circle C at the point Q. And then we're going to try to show that if it's tangent, then the segment PQ will be perpendicular to the line L, and if the line is perpendicular, then the line is tangent. So let's go ahead and do this. Let's start with 2 implies 1. Let's suppose that the line PQ is perpendicular to L. And then let R be any point on L that's not Q. So R could be some point out here, say. Now, because we've assumed that P and Q are perpendicular to each other, that means that we've got a right angle there at Q, which means that now we can construct a nice right triangle PQR. Now, since triangle PQR is a right triangle, and the segment PR is the hypotenuse, that means that the segment PR is greater than the segment PQ. The hypotenuse is the longest side in a right triangle. So PR has to be greater than PQ, which means that the distance from P to R must be greater than the distance from P to Q, which is equal to little r by definition. So that means that R is not in the circle, because the distance from P to R is greater, P to big R is bigger than little r. Now, since this holds for all points R in the line other than Q, that means that the intersection of L and C can only be the point Q. That's the only point we can have. Okay, so that gives us one direction of the proof. So for the other direction, rather than proving 1 implies 2, we're going to prove the contrapositive of that. We're going to show that if 2 doesn't hold, then 1 doesn't hold, and that'll finish up the proof. For this, let me get a new page, and we'll say, so now let's suppose that the line PQ is not perpendicular to the line L. So the picture here is that we've got the line L, and we've got the point Q over here, got the point P in the center, and we have assumed that the line PQ is not perpendicular to the line L. So let's let R be in L such that the line PR is perpendicular to L. We know such a point exists, so that's going to go right there. And once again, we have a triangle built. Now, what we would like to show based on this graph is that there's some other point. We're trying to prove that the line L is not tangent to C, to the circle, so we're trying to find basically this other point that we can see on the diagram. We're trying to basically show that it exists. So let's do that in the following way. So let's let T be in L such that, based on the diagram, we want it to be that R is between T and Q, and we want the segment RT to be congruent to the segment RQ. There's some symmetry that we're basically taking advantage of here. So now let's see what that does. So now we have that angle PRT is congruent to angle PRQ, since they're both right angles, and we have that segment PR is congruent to segment PR, of course, because congruence is reflexive. So by side angle side, we have that the triangle PRQ is congruent to the triangle PRT. Therefore, the segment PT is congruent to the segment PQ. Hence, that means that the distance from P to T is equal to the distance from P to Q, which is little r. Thus, that means that T belongs to the circle, because the only thing that defines the circle is being a distance of little r away from P. So in particular, this means that both Q and T lie in both the line and the circle. So in particular, this means that L is not tangent to C, which finishes the proof. So we have an equivalent condition for what it means for a line to be tangent to a circle. In order for a line to be tangent, it must be perpendicular to the radius of the circle that goes to the point that it intersects, or to a point where it intersects the circle. That's the only way to get a tangent line. All right, so let's talk about chords of a circle now. We can see theorem 99, which is a surprisingly, it's surprising in its applications of how useful it can be. So let C be the circle with center P and radius R. Let's let the segment QR be a chord of C. L a line, coplanar with C, and T a point such that L intersect the segment QR equals only T. So in particular, the segment QR can't be a subset of L or anything like that. Oh, furthermore, we need the segment QR be a non-diameter chord. So we want a chord that's not a diameter. Then we have a statement that's not the following are equivalent, but we're going to have three statements, and if any two of those statements are true, then the other one has to be true also. If any two of the following are true, so is the third one. So the three statements that we have are that L is perpendicular to the line QR. We have number two, that T is the midpoint of the segment QR. And number three, P, the center of the circle, belongs to L. If any two of these statements are true, then the third one has to be also. So let's sketch out what we're saying here, basically. We've got a point P, and we have a chord of the circle, and then we've got a point T on the circle, and then a line L. And I'm going to draw this in the situation that satisfies all three of these requirements. Right, so we've got three things going on here. We've got that the line L is perpendicular to the line QR. We've got that the point T is the midpoint of the segment QR. And we have that the line L contains the center P of the circle. And the statement says that if any two of these hold, then the third one has to hold as well. So let's see how we do this. And we're basically just going to go by cases. There are three different ways of choosing two of these statements and proving the other one. Oh, sorry about that. Okay, so case one. Let's suppose that T is the midpoint of the segment QR and that P belongs to L. So let's suppose that we don't know that the line L is perpendicular to the line QR, and let's prove that. So now, since PQ has length little r, which is the same as the length P capital R, we have that the segment PQ is congruent to the segment PR. So we're drawing in a couple of new segments here, which we see are congruent. So the segment PQ is congruent to the segment PR. And then also we have that TR is congruent to TQ, since we've assumed that T is the midpoint of the segment QR, and the segment PT is congruent to the segment PT by reflexivity. Thus, we have that the triangle PRT is congruent to the triangle PQT. Hence, we have that the angle PTR is congruent to the angle PTQ, and these form a linear pair. Hence are right angles. We're going all the way back to the original definition of right angles here. The two angles at T form a linear pair and are congruent, therefore they're right angles, which means that, of course, L is perpendicular to the line QR. So that's case 1. Let's look at case 2. So let's now suppose that L is perpendicular to the line QR. Whoops. Let's suppose L is perpendicular to the line QR and P belongs to L. So we've got a similar setup here. In this case, we're trying to prove that T is the midpoint of Q and R, of the segment QR. So now, as above, we have that the segment PR is congruent to the segment PQ, and we have that, again, the segment PT is congruent to the segment PT, and we have that angle PTR and angle PTQ are right angles. Thus, by the Hypotenuse Leg Theorem, we have two right triangles here. Their hypotenuses are congruent and one of their legs is congruent, and therefore we have that triangle PTR is congruent to triangle PTQ. Thus, that tells us that TR is congruent to TQ, which shows us that T is indeed the midpoint of the segment QR. So, now for case 3, let's let L be perpendicular to the segment, to the line QR, and let's let T be the midpoint of the segment QR. And so here we're trying to show that the center P of the circle lies on L. Now, let's use case 2. By case 2, let's look at the line PT. The line PT contains P, obviously, and goes through the midpoint of the segment QR. Oh, sorry, this is case 1, actually. Let's not be confusing. Case 1 said that if you have a line that contains P, that contains the center, and goes through the midpoint, then it has to be perpendicular. So by case 1, the line PT is perpendicular to the line QR. But since there is only one line through T and perpendicular to the line QR, we must have that L is equal to the line PT. So in particular, this means that P has to belong to L. So one of the things that I like about this proof, first of all, this theorem, first of all, I like that the statement is a little bit unusual. It's rare that you get a statement like, if some number of these statements hold, then all of them hold, other than the following are equivalent type statements where if even one of them holds, they all hold. So I like that this theorem has a bit of a different structure that way. I also like that it's proven in 3 cases where none of the cases are particularly long or complicated, but they use 3 fairly different techniques. So I just I like this theorem. Now, one thing I want to point out is that we can actually use this theorem for very practical reasons, and which have some importance to the theory as well. So, in particular, we can ask, let's suppose that I've got a circle. Is it possible for the same circle to be expressed in two different ways? For instance, can I express this circle using two different centers? Can it be the case that the circle with center P1 and some radius 1 equals the circle with center P2 and some radius 2? Can a single circle have two different centers? Well, we can actually use theorem 99 to prove that that's not the case, that can't possibly happen. So our answer is no. And the way to see that is to see that we can actually determine the center of the circle just by knowing the points on the circle in the following way. We can create a chord of the circle. It can be any chord that we want. And we'll take the midpoint. We know how to find the midpoints of segments. And then we know that there is some line through this chord which is perpendicular to it. And let me adjust that to the right spot. We know that there exists some point here. And by theorem 99, the center of the circle lies on L, lies on this line. Now, that doesn't, of course, narrow things down completely. There are lots of points on the line L. The point is, we can do this again. Just take almost any other chord in the circle, and the fact that I hand drew this means that this isn't going to be real perfect. But you can take any other chord, find its midpoint, and construct the line that's perpendicular to it. And let's call this line L prime. And it's perpendicular also to this second chord. So by theorem 99, the center lies on L prime also, because L prime is a line which passes through the midpoint of a chord and is perpendicular to the line containing that chord. But that means that the center of this circle has to lie on both L and L prime. And something that we know from the very first day of class is that two lines intersect in at most one point. So this means that there in fact is only one center for any given circle. You can't construct a situation where there's more than one center to a circle. Once you have that the center of a circle is unique, that also means that the radius of the circle is unique. Because if any two descriptions of the circle have to start with the same point, well, then they also have to use the same distance, because the distance is just whatever the distance is. Measure the distance from the center out to any point on the circle, and that's the radius of the circle. So, in other words, if CP1R1 does equal CP2R2, then that means that P1 has to exactly equal P2 and R1 has to exactly equal R2. So if either one of those two conditions are different, then the two circles are distinct. They contain different points in them. So this is an application. We can, of course, use this in in real life also, if we have some sort of circular phenomenon or object and the center isn't noted, we can determine the circle by following similar setups, similar schemes. All right, so now we're going to look at a theorem which is going to require a significant result from just the theory of real numbers that we haven't used yet. So far, we haven't used anything really powerful from the theory of real numbers. We've mostly just used the fact that they can be ordered. But now we're actually going to use something powerful about them. So let's look at theorem 100, called the line circle theorem. It says if a line intersects the interior of a circle, then it intersects the circle in exactly 2 points. So in particular, if I take a line and a circle and I look at their intersection, that's always going to be less than or equal to 2. You can never have a line and a circle intersect in 3 or more points. The picture of this is pretty easy to see. If we've got a circle here, and then we've got a line that intersects the interior of a circle. I really should specify that I want the line to be coplanar with the circle. So if there's some point here that the circle contains, that's interior, or that the line contains, that is interior to the circle, then that line has to intersect the circle in exactly 2 places. Let's see how this goes. So let's let L be a line intersecting the interior of the circle C, which has center P and radius R. Now let's let Q be the point on L, be such that the segment PQ, or the line PQ is perpendicular to L. As always, this is always possible. Now, since L intersects the interior of C, we must have that the distance from P to Q is less than R. And that's because L contains some point whose distance to P is less than R, and the point Q that we've set up here is the shortest, creates the shortest distance from P to L that we can come up with. So since L intersects the interior of C, the closest approach to P must come closer than little r, which gives us the boundary of the circle. So now let's let R and T lie in the line L such that R and T are on opposite sides of Q, and the distance from R to Q is equal to the distance from T to Q, which is the square root of r squared minus the distance PQ squared. What we're trying to do basically is we're trying to construct these 2 points of intersection, R and T. And we basically come up with this by measuring how far the distance QT should be, given that we can construct this right triangle. We basically look at this and say, all right, well, these distances here should be R, and then we know what the distance PQ is, which means that by the Pythagorean theorem, we can figure out what the distance from Q to T and the distance from Q to R should be. They should be little r squared minus PQ squared. This is the step where we require some results about real numbers, namely the existence of square roots, which is a non-trivial property of the real numbers. The fact that every real number has a square root is something that's true about the real numbers, but isn't, for instance, true about the rational numbers. One could imagine trying to do a geometry in which we only consider distances that are rational. That would be very difficult to try to construct and make consistent, but one could imagine it. In such a situation where the distance between any 2 points has to be a rational number, this argument would not apply, because the square root of a rational number might be irrational. And therefore, at this point, we really are relying heavily on the properties of the real numbers, some deep algebraic properties of the real numbers. Furthermore, if one does try to do geometry in the other way, I've mentioned a few times that one can do geometry without making explicit reference to the real numbers, but in doing so you have to make certain additional assumptions that we didn't have to. If you're working in that kind of geometry, you actually have to take the line-circle theorem as an axiom. You can't prove this if you don't have something like the structure of the real numbers to fall back on that allows you to construct these points R and T. We do, however, we are working with the real numbers, we're taking those for granted, and so we can look at the number r squared minus pq squared. We've just shown that pq is less than r, therefore r squared minus pq squared is positive, therefore it has a square root, and therefore we can construct the points r and t that are a distance of the square root of r squared minus pq squared away from q. So it remains to show that these points r and t that we've constructed actually do lie on the circle C. The only way we have of showing that a point lies on the circle is by showing that it sits the appropriate distance away from the center. So now, by the Pythagorean theorem, we have that the distance from P to T squared is equal to, so the distance from P to T is the hypotenuse of the right triangle PQT. So it's going to be the PQ squared plus TQ squared. We've constructed TQ so that TQ squared is r squared minus PQ squared, and therefore this all winds up just being r squared. Hence, because all numbers in sight are positive, PT actually equals r, so T belongs to the circle C. And completely similarly, R belongs to the circle C. So we've shown that if the line L intersects the center, or the interior rather, of a circle, then it intersects that circle in 2 points. What we need to show is that it intersects the circle in exactly 2 points. That is, that there isn't some other point that that also lies on the circle. So let's handle that. So now, suppose there exists a third point U that lies on L and C together. Now, this U could be on either half of the line L, separated by Q. For convenience, without loss of generality, we may assume that U belongs to the ray QR. If it lies on the other side, then just do the argument we're about to do, just replace all your R's with T's, because in that case it would be on the ray QT. Now, if U lies between Q and R, then let's see what the figure is that we get, and I'm gonna sort of blow up the figure for that situation. So in that case, we would have the following. We'd have the point P, we've got the point R, the point Q, remember this is a right angle, and the point U. Furthermore, we have that the distance from P to big R is little r, and the distance from P to U is little r. Now this figure should allow us to come up with some sort of contradiction. And we can see that it's going to be based on the exterior angle theorem. So notice that the triangle UPR is an isosceles triangle, and therefore these two angles have to be congruent. However, notice that the angle here at U is also an exterior angle to the triangle PQU, which is a right triangle. Therefore, the angle at U, the blue angle at U, needs to be obtuse, but you can't have two obtuse angles in a triangle. That's going to be our contradiction. So if we have QUR, then that means that the angle PUQ is obtuse, since it is an exterior angle to the triangle PQU. And then since PU equals R, which equals PR. Oh, sorry, there's actually a, oh no, we'll do it the way that we said. Since PU, the distance from P to U is equal to R, which is the distance PR, that tells us that triangle PRU is an isosceles triangle. And so that means that angle PRU must be congruent to angle PUR. And I realized that I made a typo up above. I wrote that PUQ is obtuse. No, PUR is obtuse, because that's the actual exterior angle to the triangle PQU. So we have that angle PRU is congruent to angle PUR. So that means that angle PRU is obtuse, a contradiction, since triangle PUR cannot have two obtuse angles. Now, if U doesn't lie between Q and R, then we might have that R lies between Q and U. In this case, we can do something very similar. And I'm not going to write out the whole argument again. We're just going to see what the picture is. And the picture is almost exactly the same. We've got P, Q, only now this time we've got R here, and we've got U here. And again, we've got that the distance PR and the distance PU are supposed to be the same. And again, we get that the triangle PRU has to have two obtuse angles in it, a contradiction. So we'll just say if QRU, a similar contradiction arises, that means that we can't have that R is between Q and U, we can't have that U is between Q and R, and so the only thing that's left is for U to actually equal R. And thus this shows that if T if the line L contains any points on the circle C, then they must be either equal to R or T. So that means that L intersect C has to exactly equal R and T. It must have two points on it. So a line can only intersect a circle at 2 points. That's what we have shown. Okay, so the next thing we want to talk about is arcs of circles. And arcs of circles are going to be sort of like segments. Arcs of circles are going to be analogous to segments of lines. They're going to involve part of a circle only. The arc is actually a lot easier to intuitively describe than to explicitly define. But let's do our best to try. Definition 101. Let's let C be a circle with center P and radius R be a circle, and Q and R points in C. The angle QPR is a central angle of C. So let's get a picture here and annotate it as we go. We've got Q, we've got R, and then we've got the angle QPR. So it's called a central angle because its vertex is at the center of the circle. Now, if P, Q, and R are non-collinear, which is what we need in order for us to have the angle QPR, as in our picture here, the minor arc QR, so the notation is QR with sort of this arcing sort of rainbow shape above it, is the circle intersect the interior of the angle QPR and then unioned with Q and R together. So let's see that here. I'm going to illustrate it in blue. Let me get a thicker line here. Haha, that is too thick. So this set of points here, going out to Q and out to R, and including everything in the interior of the angle QPR that's on the circle, is the minor arc. The minor arc QR. We can also define the arc going the other way, sort of the complement to this, though not quite. If P, Q, and R are non-collinear, the major arc QR is C without the interior of angle QPR. So I'll do that one in red. So the difference between the minor arc and the major arc is whether they are including or excluding the angle, the interior of the angle here. Intuitively, based on notation and ideas we have from trigonometry and such, a major arc is going to be one that goes more than halfway around the circle, whereas a minor arc is one that goes less than halfway around the circle. Now, this is the major arc QR. Now you'll notice that we're using the same notation here for the minor arc and the major arc, and it's difficult to find really good notation for this. We will have ways of specifying which we mean. We will not have to leave things ambiguous. One advantage to keeping the same notation here is we're actually going to have lots of theorems that apply equally well to major arcs and minor arcs, and so it makes the statement of them a lot easier when you can just use the single notation for both of them. Now, if we do have that P, Q, and R are collinear, so if P lies between Q and R, then the two arcs are going to be half circles. Let me draw a smaller one down here. Q, P, R. This one is fairly intuitive, but again takes a little bit of work to write down explicitly. And so here we're going to have two half circles. Now in this case we don't have an angle QPR to work with. So if QPR is the case, then there are two half circle arcs QR, one on each side of the line. Now, a few more things. In order to remove ambiguity, one of the things that we'll do is get another piece, another point in the notation which tells you something in the arc. So the notation Q T R with an arc means the arc QR containing T. So if we put some more points into this notation, let me put a T here and a U here and a V here and a W here, then we have that this minor arc QR that we had before could also just be written as QTR, and that actually eliminates any ambiguity here. And the major arc QR here can also be written as QUR because it's the arc going from Q to R which contains Q. And then similarly we've got the arc QVR on top of the bottom diagram and QWR way down at the bottom. So we can use these pieces of notation in order to describe our arcs without ambiguity. All right, now the next thing we want to do is to define measures of arcs, because it's going to turn out that measures of arcs and measures of angles are going to be connected to one another. The measure of an arc QR is given with the following formula. The measure of the arc QR is equal to, and we're going to have three different cases. If the arc QR is a minor arc, then the measure of angle QR is just the measure of the angle QPR. It's the measure of the angle that sort of defines that arc. On the other hand, if QR is a major arc, we have that the measure of the arc QR is 360 minus the measure of angle QPR. Essentially what we're doing here is we're saying that the whole circle is 360, has measured 360, and then if you're a minor arc, less than half the circle, then your measure is the measure of the angle that you create, and if you're a major arc, well, you're exactly what you need to be so that the sum of those two, of the major and the minor arc, is exactly 360. And along those same lines, we have that the measure of the arc QR is 180 if the arc QR is a half circle. Defining the measure this way allows us, again, to connect it up to the measures of angles. And working with measures of angles has arithmetic that behaves as you would expect. So let's look at theorem 102. If arc QR and arc RT are arcs, and they only overlap at the point R, their intersection is only the point R, then the measure of the arc QRT is equal to the measure of the arc QR plus the measure of the arc RT. So the picture for what's going on here is good to keep in mind. So let's say we've got the points Q, R, and T, and we're looking at the arcs QR and the arc RT. And what this theorem is saying is that if we look at the whole arc QRT, that has some measure, and it's equal to the measure of the two arcs individually, making it up, assuming that the red and blue arcs don't overlap anywhere except at R. The thing that makes this theorem a little bit of a hassle to prove, and why we're not going to do it now, is that there are actually lots of different cases to work on, depending on whether the resulting arc that you get is major or minor. In this case, we can see that the resulting arc is major, which means that in this situation, we have that the measure of arc QRT is equal to 360 minus the measure of angle QPT. But in this case, we have that the arcs QR and the arcs RT are minor arcs. So we have the measure of, oh, I should have used the wrong notation here. We wanted to say the measure of the arc QRT is 360 minus the measure of the angle QPT. We have that the measure of the arc QR is equal to the measure of the angle QPR, and the measure of the arc RT is equal to the measure of the angle RPT, because both of these arcs are minor arcs. And so we need to somehow show that this quantity here is equal to the sum of these two quantities, and it's not at all clear how to go about it initially because we don't have any of the same angles involved. In our setup over here, you'll notice we don't even have any linear pairs we can take advantage of. But as it turns out, that's exactly what we need to do. As we go through and, or as one goes through and solves this, what you have to do is essentially draw this line here through Q and P and break up the problem further and say that, all right, well, we've got this angle that defines QR, but then the red arc, which is defined by the angle RPT, we're going to break up into two angles and work with each of those. And then finally, we're going to connect all that up to the angle QPT, which defines the final angle here. So let me just sketch out what's going on here by giving these names. Let me give alpha, beta, gamma, and delta here for the measures of the various angles involved. So what we have is that the measure of angle QRT is 360 minus the measure of angle QPT, which is delta. And the measure of angle QR is just alpha, and the measure of angle RPT is beta plus gamma. But then we use the fact that alpha plus beta is equal to 180, and that gamma here is equal to 180 minus delta, because gamma and delta form a linear pair. And therefore now we can see that 360 minus delta does in fact equal the alpha plus beta plus gamma that we had here. And you need to do this sort of argument 5 times in order to consider all of the various ways that things can combine together. This is the basic idea behind it. I don't feel that going through all of the details will be particularly illustrative of what's going on now that you see the general strategy. However, it is good practice for writing proofs and getting your head around what these arc measurements and angle measurements really mean and how they interact with one another. So now we want to consider how circles interact with angles whose center is not in, or whose vertex is not at the center of the circle. And there's going to be a couple of different kinds of relationships we're going to look at. And definition 103, I'm going to do first by picture. And I'm going to have 2 pictures here to look at. So the first is I'm going to look at an angle of this form. So we've got we'll have Q, R, and T, and we'll talk about angle QRT. And we'll say that angle QRT is inscribed. Inscribed in the arc QRT. In this case, the arc QRT looks like this, and the angle QRT is said to be inscribed in the arc QRT, and that's whenever Q, R, and T all belong to the circle. So that's a term we have for angles that are whose vertex is on the circle and whose rays also intersect the circle in another point. Now we may also have angles that intersect the circle in different ways. So, for instance, we could have an angle like this, where the center is not, or the vertex is not at the center, or anywhere on the circle. And we can also, I want to look at angles that go like this. Now in this case, we want to look at a certain arcs in this problem. Look at this arc here, and this one down here. These are all arcs that we're going to say are intercepted by these angles. We say these are intercepted by the angle. So let me go ahead and give these some names also. A, B, C, D, E, F, just so that we can talk about them carefully. We will say that the arc AC is intercepted by the angle ABC. And when the 2 points that you've noted are on the circle, then that's easy to describe. On the other hand, if we've got the angle DEF, that intercepts 2 arcs. So we will say that GH, the arc GH, is intercepted by the angle DEF if G lies in the ray ED, H lies in the ray EF, and we have that the arc GH lies in the angle DEF union with the interior of the angle DEF. So intuitively, an arc is intercepted by an angle if it lies inside that angle. But we do want to be precise here. The 2 endpoints of the arc have to be on different rays of the angle. So, for instance, if we had a situation like this, if we had some angle like that, we would not say that this arc here is intercepted by the angle, because it starts and ends at the same ray of the angle. In order for an arc to be considered intercepted by an angle, it has to go from one side of the angle to the other. And what we're going to be interested in a lot is the intercepted arcs of inscribed angles. We can combine these two notions together and talk about those. And in particular, we're going to have theorem 104, which gives us the relationship between them. The measure of the intercepted arc of an inscribed angle is twice the measure of the inscribed angle. So we have ways of measuring arcs and we have ways of measuring angles. And what this is saying is that if you compare the measures that you get when you take an inscribed angle, say A, B, C, and then you look at the measure of the inscribed arc to that, then the measure of the arc, the measure of the arc AC is equal to 2 times the measure of the angle ABC. And we can use this to prove things about similarities of triangles that you get by connecting up various points on a circle. Let's look at the proof of this, although again there are several cases. We're just going to look at one of them. And the cases depend on where the center of the circle is in relation to everything else. So let's go ahead and handle the case where the center P actually lies on one of the rays of the angle. So let's let C be CPR and let A, B, and C. Oh, I shouldn't use C. We're already using C. I'll use D. And let A, B, and D be in the circle C. So we want to prove that the measure of the arc AD is equal to 2 times the measure of the angle ABD. So case 1, let's suppose that P actually lies in the segment BD. Let's suppose that BD is actually a diameter, and I'm going to go ahead and redraw my figure that way. All right, so now we're looking at this arc. So in order to get at this, of course, we're going to need to get at the measure of the arc AD, which means we're going to need to know about the measure of the angle APD and relate that to whatever else is going on. So notice that triangle APB is isosceles. Since the distance from P to A is the radius of the circle and the distance from P to B is the radius of the circle, that means that we can get a relationship between these two angles are congruent to one another. And so that means that angle PBA is congruent to angle BAP. Now, by the exterior angle theorem, we have that the measure of angle APD is equal to the measure of angle ABP plus the measure of angle BAP. So the exterior angle theorem says that this exterior angle at P is equal to the sum of the measures of the remote interior angles. Because we're in Euclidean geometry, we can get that equality. Now we have that these two angles are congruent. So this is 2 times the measure of angle ABP. But then we have that the arc AD, the measure of the arc AD is equal to the measure of angle APD, which we've just shown is 2 times the measure of angle ABP, and the measure of angle ABP is the same as the measure of angle ABD because they are the same angle. So that proves it in the case of the center being on one of the rays of the angle. There are 2 other cases, one where the center lies in the interior of the angle and one where the center lies outside the interior of the angle. So we'll just sketch the proof of that. So case 2, let's suppose that P is in the interior of angle ABD. So in this case, we have something like P, A, B, D. And here, what we want to do is to construct a line that goes from B through P and gives us another point E over here. And so what that does is it splits the problem into 2 pieces, each of which we can handle by case 1. So by case 1, the measure of arc AE is equal to 2 times the measure of angle ABE, and the measure of arc ED is equal to 2 times the measure of angle EBD, and therefore we have that the measure of the arc AD, which is the measure of arc AE plus the measure of arc ED, is equal to 2 times the measure of the arc ABE, angle ABE, plus 2 times the measure of the angle EBD, and by angle addition, this is 2 times the measure of angle ABD. So we're basically just applying case 1 to the angle ABE and the angle EBD, and then combining those together and seeing that, yeah, the arithmetic works out. And then case 3, in this case, we've got something like the following, where P is completely outside the angle. And this goes similarly. You construct this again, construct this line again from B to P to E, only now you're going to use subtraction. You can apply case 1 to the arc AE, apply case 1 to the arc DE, and that'll give you the measure of the arc AD. And so a similar arithmetic manipulation gives you the equality that you want there. So this relationship between the measure of an inscribed triangle and the measure of the intercepted arc can be used in a number of different ways. One of the most fun is the following. Let's look at theorem 105. If A, B, C, and D are points on a circle, and if the segment AC intersects the segment BD in a point E, then the triangle ABE is similar to the triangle DCE. Let's look at the picture to see what's going on here. We've got A, B, C, and then let's do D over here. Try to get some extreme things here. All right, so this is the figure that we're looking at. This is what's given by the statement of the theorem, and the claim is that the two triangles that we've constructed by connecting up these points this way are in fact similar to one another, which is certainly not obvious, but let's see how this goes. Easy one out of the way, we have vertical triangles, and vertical triangles are vertical angles, sorry, are congruent. So since angle AEB and angle CED are vertical, they are congruent. Okay, that's great. So the next thing that we want to do is to consider the arc from A to D. Now, of course, we don't know what the measure of this arc is, but we do know how it relates to the two angles that intercept it. So we have that angle, we have that angle ABD intercepts arc AD, and hence we have that the measure of arc AD equals 2 times the measure of angle ABD. But similarly, the angle ACD intercepts the arc AD. Therefore, we have that the measure of arc AD is equal to 2 times the measure of angle ACD. But that means that because both of these expressions are equal to the measure of the arc AD, they're equal to the same thing, and therefore we have that the measure of angle ABD is equal to the measure of angle ACD. So in particular, this means that the angle ABD is congruent to the angle ACD. But that's good enough. We have angle-angle as a similarity theorem. So hence, by angle-angle, we have that triangle ABE is congruent to triangle DCE. Sorry, not congruent, I'm being silly, is similar. They're definitely not congruent. And so that means that you, of course, have all the relationships between them, that the ratios of corresponding sides are equal, and all the other nice things that we get out of similarity of triangles. Our last section for this video is called the Two Circle Theorem. Now, the Two Circle Theorem is one that tells us how two circles can intersect one another. Before we do that, we actually need a theorem on triangles. Now, we've had the triangle inequality since early in the course, which says one way of interpreting what it says is that if you've got a triangle, then every side, the length of every side is less than the sum of the lengths of the other two sides. But it turns out that there's a converse to this as well. If you pick any three numbers, positive numbers, such that the largest is less than the sum of the two others, then you can construct a triangle with those side lengths. So theorem 106 says that if A, B, and C are positive numbers, in fact, let me abbreviate this slightly. So if 0 is less than C, which is less than or equal to B, which is less than or equal to A, are real numbers, and we have that A is less than B plus C, then there is a triangle with side lengths A, B, and C. So for the proof here, I'm going to work it a little bit backwards. You can find a formal proof in the notes. What I want to do is talk about how we actually come up with it. So we know that we're going to try to construct a triangle with various side lengths. So we can think about what sort of construction options are available to us in geometry. We want to construct a triangle like this with side lengths A, B, and C. Now, usually trying to build a triangle off of the largest side is the way to go. So the way the formal proof might work is something like, let P and Q be 2 points such that the length of the segment PQ is A. And then we got to try to somehow come up with this point R up here at the top of the triangle. Now, the types of constructions that we have available to us, well, we can certainly build segments and angles. Now, building angles isn't too helpful here, at least not at the beginning. If we wanted to try to say where our side with length B should be, we would need to know at what angle are we going to construct it. And without going into some trigonometry, law of cosine, stuff like this, then we don't have a good way of doing that. We could approach it using the law of cosines, but frankly, that's bringing in a lot more technology than we need here, and so we're going to do it a different way. What we can do instead, using basically just the Pythagorean theorem, is try building this point here. Let's call this point T and go up like this. And if we could figure out where T is supposed to lie on the segment PQ and figure out how tall the segment TR is supposed to be, that should be enough to build our triangle. And if we can balance everything out, if we can figure out how far over this should be, then we have a chance at getting to where we need to go. So the way that we might do this is we might let x be the distance from P to T, and therefore a minus x is the distance from T to Q. Now the length of T to R we might label D, and we want to say we want to prove that we can find an x and a D making this figure work. Given that we are going to put a right angle there, that's usually what we want to do. And putting a right angle there, of course, means that we can use the Pythagorean theorem. So let's see what would have to be true about x and d in order to make this figure work. Well, we've got two right angles that we can use. Let's start with the triangle PTR. Based on the triangle PTR, we would need to have that x squared plus d squared equals b squared. And based on the other triangle, QTR, we would need that a minus x squared plus d squared is equal to c squared. And we want to find an x and d that make both of these things happen. Now we can sort of solve the left-hand equation for d. So we have d squared is equal to b squared minus x squared. And so we can use this to find d if x winds up being less than b. So if x is less than b, then we can use the left-hand equation in order to determine d. Because of course d has to be positive. But assuming we do that, if we can set x to be less than b, then we can take this over into the other equation and get that a minus x squared plus b squared minus x squared is equal to c squared. So we want to find an x that makes this happen. So let's go ahead and expand this out, see what we get. So we get a squared minus 2ax plus x squared plus b squared minus x squared equals c squared. Now there's a lot of cancellation here, a lot of stuff that happens, but if we wind up solving for x, what we get is that x is equal to a squared plus b squared minus c squared all over 2a. And so this is great. We can just let x equal a squared plus b squared minus c squared over 2a, and then define d to be the square root of b squared minus x squared. But we have to be careful. We know that we can't just choose any three numbers a, b, and c to make this work. The condition that a is less than b plus c has to show up somewhere. And where it shows up is in what we need x to satisfy. We need x to be less than b. We also need for x to be greater than 0. For this figure to work, x needs to be the length of a segment, and therefore it has to be greater than 0. So basically, we need to show that as long as a, b, and c satisfy the conditions above, this expression, a squared plus b squared minus c squared over 2a, is strictly between 0 and b. Let's move that to the next page. So we have x is equal to a squared plus b squared minus c squared all over 2a, and we want to show that x is strictly between 0 and b, given that we have that c, b, and a are all positive, a is greater than the other two, and a is less than b plus c. All right, so one part of this is pretty easy. So since a is greater than or equal to c, and b is greater than or equal to c, we have that a squared plus b squared minus c squared. Well, b squared minus c squared has to be greater than or equal to 0. So a squared plus b squared minus c squared is greater than or equal to a squared, which is certainly greater than 0. So that checks out. So this means x is greater than 0. To see whether this x value is less than b, we just need to do some manipulation. So we get a squared plus b squared minus c squared over 2a is less than b, if and only if a squared plus b squared minus c squared is less than 2ab. And now we can do a little more manipulation around. This happens if and only if a squared minus 2ab plus b squared is less than c squared. Now the left-hand side of this can factor. This is a minus b squared. Now, we know that a is at least as big as any of the others. A is greater than b, and everything in sight is positive. And so if we've got two non-negative numbers, a minus b and c, and we know that their squares have a particular relationship, this happens if and only if they themselves have that relationship. So this inequality happens if and only if a minus b is less than c, which happens if and only if a is less than b plus c, which indeed is what we've got. Now, of course, the direct proof sort of works backwards on all of this, but this is the main idea behind showing why what we can do can work. So what this shows is that if we define x this way, if we start with a segment of length a, and then we choose a point t on here where the distance from p to t is this value of x, which we defined above, and then if we do that, then x is less than b, which means that we can set t to be d, which is the square root of b squared minus x squared, which is defined because x is less than b. And then once we do that, we have we can certainly construct this triangle, and then the Pythagorean theorem will show us that indeed we get that the side length is b here and c here. So that allows us to construct a triangle with any side lengths we want, so long as the largest side length is less than the sum of the other two side lengths. So with that, we're finally able to get to the Two Circle Theorem. So theorem 107 is called the Two Circle Theorem. So let C be the circle with center P, radius R, and let's let C prime be the circle with center P prime and radius R prime, be coplanar circles. Circles such that each of the numbers R prime and P prime, the distance between the two centers, is less than the sum of the other two. In this case, we have that C and C prime intersect in exactly 2 points. So this tells us that two circles can intersect in only 2 points, assuming these conditions hold. So let's see how we can go about proving this. So the picture here, and it's difficult to draw a picture that illustrates the full reasoning because it's very intuitive that what we're saying is true. However, we can go about it this way. By theorem 106, there is a triangle ABC with the length AB equal to the length PP prime, the length AC being R, and the length BC being R prime. Essentially what we're going to do is we're going to copy this triangle. We know it exists somewhere down here. There's some triangle down here that does what we say. And what we're going to do is we're going to draw a congruent copy of it over here onto these two triangles and use that to show that the other vertex of the triangle has to lie on both circles. So let H1 and H2 be the half planes defined by the line PP prime. So we'll say H1's up here and H2's down here. Now, by the angle segment construction theorem, there is a unique point Q in H1 such that the angle P prime PQ is congruent to the angle, is congruent to the angle BAC, and where the segment PQ is congruent to the segment AC. That's our standard angle segment construction theorem. So that's going to be this point up here. We're going to call that Q. And we know that the length of AC is R. That was part of our construction. And so that length is R as well. And we have that this angle and this angle are congruent, the angle at A and the angle at P. So now, since PQ is equal to AC, which is equal to R, the point Q lies on the circle C, because it's a distance of R away from P. Now, let me go to the next page. Let's grab these figures. Now, we have that by side angle side triangle QPP prime is congruent to triangle CAB. We've got the two blue triangles in our figure are congruent to one another. And in particular, this means that the segment P prime Q is congruent to the segment BC. So in particular, this means that the distance from P prime to Q equals the distance from B to C, which is, by construction, R prime. Thus, that tells us that Q is on the circle C prime. So therefore, Q is in the intersection of C and C prime. Now, if R is any point in H1 that lies in C and C prime at the same time, then we would have that PR the distance from P to R is equal to R, which is equal to AC, and the distance from P prime to R would be equal to little r prime, which is equal to BC. And so this would tell us that the triangle PRP prime would be congruent to ACB by side, side, side. If I chose some other point R that also lay on both circles, then it would have exactly the same side lengths as the triangle ABC. So thus this means that the angle P prime PR would be congruent to the angle BAC, and the segment PQ would be congruent to the segment AC. But by the uniqueness of angle segment construction, this means that R actually has to equal Q. This means that there is only one point in the intersection of the two circles in H1. So there is only one point in H1 and in C and in C prime. And then similarly, there is one point in H2 intersect C prime. We're just going to construct a copy of the triangle ABC on the bottom half of the diagram rather than the top. And then if we had any point that lay on both circles and on the line between them, that is not neither in H1 nor H2, then that would mean that the distance from P to capital R here would be little r, and the distance from P prime to R here would be little r prime, and R would be between P and P prime. So in particular, this would mean that, or I should say not necessarily between them, but the point is that R, P, and P prime would have some sort of betweenness relationship. Let me go ahead and just do this on the next page. This is the last statement that we need. So if R lies in the two circles and on the line from P to P prime, then that means that R, P, and P prime have some betweenness relation. And so the numbers RP, which is R, RP prime, which is R prime, and PP prime have the largest equal to the sum of the smallest. Equal to the sum of the other two, I should say. Because if we've got R, P, and P prime on the line. Let's say we have P, P prime. Let's say we have R over here. There's some sort of betweenness relationship. We know that the distance from R to P is little r. The distance from R to P prime is little r prime. And then, of course, we've got the distance from P to P prime. And no matter how you arrange these 3 points, the betweenness relation says that whatever the largest one of them is, it's the sum of the other two numbers. which is a contradiction, because we assumed that the largest of these numbers is strictly less than the sum of the other two. So this finishes up the two circle theorem. It says that there are lots of ways for two circles to intersect. We could have a situation like this. We could have the situation like this, which we saw before. But if the three numbers, the two radii and the distance between the centers, have a triangular-like relationship between them, if you could draw a triangle with those three side lengths, then the two circles intersect in exactly 2 points.